Bismillahirrahmanirrahim. Rabbi israh li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Inshallah, we shall continue our lesson on chapter 2 now, entitled as Motion in 1 and 2 Dimension. So before we begin to the details of the formula, of course we need to recall few terms that we use to in motion. The most important and the very first is about position. Position is defined as the location of particle with respect to the chosen reference point. So we have three different ways to explain or to state the motion of an object. For example, a car move from position A to position B and then reverse back to position C, D, and reaching F. So whether we put it in terms of pictorial like this, or we call it motion diagram, or we also can have a tables, or also in terms of graph. So the representation just now named as pictorial representation, this one, tabular representation, this one, and graphical representation in terms of graph. Second term is about displacement. Displacement, symbolized normally in terms of delta x of particle, is known as change in position in a given time interval. Alright, so the delta x is defined as x final minus x initial. And we have another term is average velocity. Average velocity is known as delta x over delta t. For example, for the motion of the car just now from position A to position B within 10 seconds is calculated as 52 meter x final minus x initial, which is 30 meter over the time interval, which is 10 minus 0. This gives us the average velocity is 2.2 meter per second for the car to move from point A to point B within 10 seconds. Now, we may also calculate the speed. Instead of only taking care of the velocity, we may also take a look on the speed. As we know, speed talking about magnitude of the velocity without concerning about the direction. So we need to know the displacement, the average velocity as we calculated just now, and now we go for the average speed of the car, let's say from point A until point F, right? So in terms of displacement, we are going to calculate x final, which is xf, minus x initial, which is at point A. So if we refer to the either in terms of a motion diagram or pictorial or in terms of graph, we see at position A, the position of the car is 30, and for the point F, the position of the car is negative 53. So if we're talking about delta x, it must be x final, negative 53, minus the x initial, which is 30. That is how we have the displacement equivalent to negative 83 meter. What does that mean by negative? It means that to the left, because the car is reversing to the back. Now, for average velocity, it's defined as delta x over delta t, right? So if we substitute the information of delta x over delta t, we will get negative 1.7 meter per second. What is the meaning of this? In terms of average velocity, starting from point A until point F, the car has 1.7 meter per second of velocity to the left. However, when we deal with the average speed, the delta x is not the displacement. The delta x must be the distance traveled by the car. So, when we want to determine the distance traveled by the car, we are not concerning whether the car moving to the right or to the left. We are only concerned about the total distance traveled by the car. So from point A to point B, the car has traveled for 22 meters. From point B to point D, the car has traveled 52 meters. You may take a look on this value as well, on how I get this information. And from point D to point F, the car has traveled 53 meters. So when you add up all these three, you will get 127 meters of total distance traveled. Over the time taken is 50 seconds. So this is 2.54 meter per second as the average speed of the car, starting from point A until point F. So let's take a look on the example 2.1, the tortoise and the hare. A turtle and a rabbit engage in a foot race over a distance of 4 kilometers. The rabbit runs 0.5 kilometers and then stop for 90 minutes nap. Upon awakening, he remembers the race and runs twice as fast, finishing the course in a total time of 1.75 hours. The rabbit wins the race. Oh, it's not the story of that tortoise win the race, isn't it? A. Calculate the average speed of the rabbit. B. What was his average speed before he stopped for a nap? Assume no detours or doubling back. Alright, so we're going to calculate the rabbit overall average speed. So when we talk about speed, again, it must be total distance travel or path length taken by the rabbit over the elapsed time or time taken to do that. Alright, so it's totally 4 kilometers and total time taken 1.75 hours. Okay, this is including from starting until the end, including the nap time. So the answer is 2.29 kilometers per hour. Part B, find the rabbit's average speed before his nap. Okay, for part B, we need to know what is the average speed of the rabbit, okay, before it takes the nap time, isn't it? So what we're going to do, we need to bear in mind that nap time is 90 minutes and total time, as we know in the question given here, total time for rabbit to finish the course is 1.75, must be deducted with the 90 minutes of nap. Okay, so if you minus 90 minutes of nap, actually the time for the rabbit in motion is 0.25 hours. This includes the first part of the motion, the race, and the second part of the race after the nap. So this is before the nap, and this is the time taken for the rabbit after the nap. Alright, and we know that time is equivalent to D over V for both case, for before the nap and after the nap. Okay, this time when we add up it must be equivalent to the 0.25 hours just now. Alright, and substitute the information of after the nap. Okay, the rabbit move twice as fast as before it takes the nap. So we know that, okay, V2 is actually 2 times of V1. So we're going to substitute the information here for V2 and here information of the D1 and D2. Okay, so simplify this equation and solve for the V1. We will see the answer is 9 km per hour. So this is on how we're going to know that the V for the rabbit, B for it takes the nap. Okay, so to know the, if let's say the question asking for the speed of the rabbit after it takes a nap, so you just double this one. Okay, so exercise 2.1, do it as your homework. Make sure you will get this answer. We will discuss in class. Same goes to the quick quiz 2.1. Okay, I want you to take this as your homework. Okay, we shall discuss the solution in our physical class. There is another term that important here, which is instantaneous. What does that mean by instantaneous? It means that at very particular time, what is the V at that particular moment, right? So if we refer to the same motion of the car as previous in example, from point A moving to point F here, okay, we have calculated the V average, okay, to this and to this. However, we haven't taken a look on the exactly, let's say 2 seconds after the motion of the car. What is the V of the car? So the green color here, the tangent line here, the information of the instantaneous velocity. Okay, so calculating the slope, okay, that is perpendicular to the time that we refer to, let's say 2 seconds, alright, will give us the instantaneous velocity, right? So the blue color represent the average velocity that we calculated just now. Alright, so if we look at this, okay, the blue line between point A and B approach the green tangent line as at point B is moved closer to point A because the time taken is very short for instantaneous. Okay, the definition of instantaneous velocity is defined as limit of delta x to the respect of the delta t whenever the delta t is very small or approaching 0. In simple, it is dx over dt. Okay, so if we refer to the information given here, we have position of the car at specific instant of time, and then we have the calculated value of the time interval, displacement and average velocity of the car of table 2.2. So here is more information given. So from the time interval, okay, what is the delta t, what is the delta x, what is the v of that particular car. So you see here x versus t graph, okay, we have the motion is in red line, okay, the slope of the blue lines average velocity are average velocities with approach the slope of the green tangent line as an instantaneous velocity. So if we want to know the instantaneous velocity at this particular time, let's say, what are we going to do? We are going to do a tangent line, okay, and then calculate the slope of this tangent line. The slope of this tangent line is the V instantaneous of particular time here. Okay, and now let's move to acceleration. First, we're going to take a look on the average acceleration. So let's say we have a car moving from point A to point B with V initial and V final, okay, within T final to T initial, okay. So the average acceleration of the car is defined as delta x over delta t. So in terms of graph, okay, moving from point A to point B, the real graph of the motion of the car actually in terms of red color here, red color line here. Okay, in terms of average, okay, that connect between point A to point B, the blue line here, give us information of the average acceleration. However, if we want to know what is exactly the acceleration of the car at point B, again, you are going to do tangent line that passing through or touching point B, and then calculate the slope. That will give you the information of the instantaneous acceleration of the car. So this is what I mean, and the formula for the instantaneous acceleration is the limit of delta Vx over delta t to the respect of delta t whenever the delta t is very small or approaching 0, or in simple is actually defined as dv over dt. Now we move to acceleration versus time graph. So how to interpret, how to convert from v versus t graph to a versus t graph. So take a look on this. Okay. Right, let's say at point A, at T, which is point A. Okay, so here is the slope. Okay, if you see the increment, okay, the same, right, throughout. If you're considering this line bigger, also the same, right, the same slope, right? The slope for this point is the biggest amount. That is why the acceleration plot in A versus T, there is the highest amount of it. Okay, and then at point B or TB, okay, if we determine the slope here, okay, there is no slope, right, because it's flat. There is no slope, therefore the value of A will be 0. Okay, how about at point C? At point C, okay, we are going to calculate the slope here, and it is negative, right? So that is why the value of acceleration at TC is negative, because the slope is negative. Okay, here flat, no slope, here positive slope. Okay, hopefully you will be able to translate the information of V versus T into A versus T graph. Now let's proceed to motion diagrams, where we're going to observe the diagram of the car. Normally from one picture to another picture, the time taken is the same. This is the key for motion diagram. The time taken for each of the picture is the same. The t is the same. So if we refer to this one, okay, the distance between the first picture to the second, to the third, to the fourth, to the fifth one, almost the same distance, right? So means that the car move at constant velocity, no acceleration. Right? And then because the diagram itself showing to us the V, okay, so we know that the V is constant, therefore the A is 0, because A is defined as delta V over delta T. Remember this. And now if we refer to diagram B, from first picture to the second picture, okay, the distance to the third, to the fourth, to the fifth, the distance is different. Okay, so means that, and the arrow of the V as well, the length of it is different. It means that the V is not constant, it's changing. Therefore there is A, and then the A is constant. Why is it constant? The increment constant. Okay, the increment is constant. And then if we refer to figure C, okay, seems like it's opposite, isn't it? It's opposite to figure B. So means that it has A, however, it's in opposite direction, or in other words, the car is decelerating, slowing down. That is why the vector of A in opposite to the vector of V. Alright. Okay, for graphical determination of velocity, if we have here x versus t, okay, if we compare to the second graph, x versus t as well, however, the shape of the graph is not the same. If we refer to this, okay, from point A to point B to point C, it's just a straight line, isn't it? However, this one will have a curved line. The average velocity between any 2 points equals to the slope of the blue line connecting the 2 points. So it is different. From A to B, the average velocity from A to C, A to D, A to E, or A to F, there are different value of average velocity. How about this one? From A to B, we are going to have only one slope, isn't it? One value of slope. From A to C, also the same value of slope. So means that the V of the object or car is constant because the V is defined as delta x over delta t. Okay, for this case, we're going to determine the slope as well, isn't it? But the slope keep on changing. This is the slope for A to B. This is the slope for the A to C. And here we have the slope of A to D. And here we have the slope of A to E or A to F. So the gradient or the slope keep on changing. It means that the velocity keep on changing. But then for this case, for figure A, okay, the V, the slope, the V, the same. The slope, the gradient from point A to point B or A to C is the same. Therefore, the V is constant. Example 2.2, slowly moving train. Okay, a train move slowly along a straight portion of track according to the graph of position versus time in figure 2.7a. Find A, the average velocity for the total trip, and B, the average velocity during the first 4 seconds of motion. C, find or calculate, determine the average velocity during the next 4 seconds of motion. And D, the instantaneous velocity at t equivalent to 2 seconds. And E, the instantaneous velocity at t equivalent to 9 seconds. So solution given here. Find the average velocity from O to C. Okay, from O to C. So connect these 2 points, figure out the slope of it. Slope of the blue line. You see, the slope of the blue line. V average from point O to C. Right? So it's delta x over delta t, where we have 10 minus 0, 10 minus 0 over 12 minus 0. So it gives us positive 0.833 meter per second. For part B, we need to find the average velocity during the first 4 seconds of the train's motion. So the first 4 seconds, still talking about average. So V average equivalent to delta x over delta t. So for the first 4 seconds, so means that it reached point A. So we have 4 minus 0, means that the time is 4 seconds. And for the position, it's 4 minus 0. So we are going to substitute it here. We will get the V average is positive 1 meter per second. For part C, we need to figure out the average velocity during the next 4 seconds. So the next 4 seconds means that from 4 seconds until 8 seconds within this duration. Okay, so means that from point A to point B. If you see here, there is no slope here. It's a flat line. So when it is a flat line, okay, the delta x is the same. In other words, therefore the delta x is 0. The x is the same means that the delta x is 0. So you have 0 of v average for point A to point B. Okay. Next, you need to find the instantaneous velocity at 2 seconds. Let's take a look. Where is 2 seconds? 2 seconds is here. So, touch the point. You're going to figure out. You're going to determine, okay, the tangent line that passing through 2 seconds, which is also this one, right? The same slope to the O to A. So O to A, it means that it's the same to this. Okay. And for E, find the instantaneous velocity at t equivalent to 9 seconds. Okay, where is 9 seconds? 9 seconds here, somewhere here, in between, right? Okay, so at this position, so you need to determine the green dash line slope, right? So delta x over delta t again. So for 9 seconds, you see the coordinate, okay, here and here for the delta x. For the delta t, here and here. So take a look on the information given to us. The delta x, 4.5 minus 0. And then this is the coordinate, okay, x-axis. Okay, and then here 9 minus 3 seconds. So we will have 0.75 meter per second as the instantaneous velocity of the car or object at t equivalent to 9 seconds. So again, exercise 2.2, do it as your homework. We shall discuss it in our class. Okay, let's move to graphical determination of acceleration. If let's say we have a car moving from point P to point Q with V initial until V final at point Q. Okay, if we represent the motion of the car into a graph of V versus T, we know that the gradient of graph V versus T going to be the acceleration, because acceleration is defined as delta V over delta T. So this is the real motion of the car. Real object actually has the V in terms of curve, not a straight line. During your secondary school, teacher normally put it as a straight line to make it easy for your level at that moment. Okay, so now you are in the university level, you have to know that the real V of a real object in a real life actually not a straight line. If we're talking about average acceleration from point P to point Q, you connect these 2 points and calculate the slope of the blue line here. That will give you the information of the average acceleration. Okay, however, if you are particularly want to know what is the A instantaneous at T final at point Q, you're going to do the tangent line, the green color one here, and calculate the slope. This will give you the instantaneous acceleration of the car at T final or Q position. Okay, this is quick quiz 2.3. Take it as your homework. We shall discuss the solution in our class. Thank you.